Hello, my name is Kevin Randall. I've been with Campbell Scientific for about 12 years. I'm part of the sales team in the infrastructure market. And recently I was in South America working with some clients doing a training. While I was working with these clients, they shared some reports of vibrating wire measurements, and it led to a really useful discussion. During that training, I reached out to Brent, who's our product manager in the infrastructure market. Brent, can you just give us a quick introduction of yourself?
Yeah, so like Kevin said, my name is Brent. I work with Campbell Scientific. I'm a geotechnical engineer, strong focus in instrumentation, UA instrumentation, and that's how I ended up here at Campbell's.
So during the training, there was some discussion about the measurement technology on vibrating wires, of how we measure vibrating wires. It's called VSPECT. So Brent, I'd like you to give us just a bit of an explanation. What is VSPECT and why is it needed?
Great, thank you. VSPECT is a patented measurement technology from Campbell Scientific. You'll find it in our vibrating wire data loggers like the CR6, the CRVW3, the AVW200, and our handheld field reader, the VW Analyzer. What VSPECT is it measures the time domain technology, which really means it measures the incoming signal as that vibrating wire oscillates back and forth. And then we perform some math on it, and we get a much clearer understanding of what the actual sensor frequency is and eliminate noise in the process. Now, with VSPECT and the different devices we have, VSPECT outputs multiple parameters on a single measurement. The two most important parameters are sensor frequency and the thermistor, if it's attached to the sensor, which it is on most vibrating wire sensors. The other parameters are diagnostics to help give you confidence that you've identified the correct frequency. Now, when you take a VSPECT measurement with like a CR6, you're only going to get a numerical response on the VSPECT parameters. With the VW Analyzer, it will actually create a measurement report for you that has those parameters, as well as a graphical image of the signal and some other metadata that's very useful, like the GPS position, who was out on site that day. And so that's what VSPECT is. Now, why VSPECT is important? First and foremost, it gives you a quality vibrating wire measurement. You can have confidence that you're reading the correct signal. A lot of other measurement technologies will have noise coming in, and it disrupts the signals, and an engineer has to go in and filter out those bad measurements. With VSPECT, you can have confidence that you're getting the right signal consistently. The noise issues that people have to filter out go away. The other thing is, especially with the VSPECT report, it gives you a quick indicator of the health of the sensor. And as you do that over time, you can see if a sensor's changing, if you need to address something, or if you need to change the measurement parameters and just get a stronger signal coming back.
So that's actually a really good thing to point out. This is what led to the whole conversation when I was in this training, was one of the clients asked, why does it matter, the sensor diagnostics? And the answer that I gave him was that the vibrating wire sensors have such a long life, they can last for decades, that it's really important to understand the quality of the sensor after it's been in the field for such a long time. And so the exercise that we did was to take a vibrating wire sensor and hook it up to the VW Analyzer and get a measurement. Now, after we did that exercise, the client said, can I share some of my reports? And we can look at what I'm seeing in the real world. So we've got those reports. They've allowed us to look at these reports. Can we pull those up? And let's talk about some of the things that help us understand the quality of the sensor and whether there's noise or anything else.
Yes.
Let's take a look at those.
Here are the reports from the training that were shared. And I want to just go through some of these and show you what we're looking at. So the first report is a very good quality sensor. It's pretty much what I'd call a textbook sensor. The lower graph shows the actual image of the sensor frequency as it's vibrating and recorded by the data logger.
So that's the time domain.
That would be what we call the time domain or the time series.
Okay.
The second graph in the middle of the report is what's called the frequency domain or the frequency spectrum. We take this time domain and we do a fast Fourier transform, and rather than look at the signal as it goes through time, we break it down into the different frequencies. So what I called this as a textbook quality sensor, that means it really has one strong frequency right here that is the sensor output.
Mhm.
It's a pretty clean sensor.
So what's the advantage of doing a fast Fourier transform on that time series data?
So a fast Fourier transform allows you to see all the different signals that are coming in. You could have a noisy environment. You could have a sensor that outputs a couple of different signals. All of those are normal. It's not necessarily a bad thing, but with the fast Fourier transform, it allows us to identify the key or the primary signal from the sensor and identify it with confidence and without the influence of noise.
So when you talk about noise, are you talking about audible noise?
So when we talk about noise with measurement systems, it's electrical noise that comes in to the data logger. When you have a vibrating wire sensor, there's a cable attached to it. That cable can act like an antenna and pick up electrical noise in the surrounding environment. You might also have a noise that comes in from the actual sensor. That sensor could be vibrating. It could have a harmonic in it. All of these noises are present in normal systems.
What could be the sources of some of that electrical noise?
So probably the most common source of electrical noise is going to be the AC power grid. You'll see that come in as a 50 hertz, 60 hertz noise, which is the frequency of the grid depending on where you are in the world.
So you would see 50 hertz or 60 hertz noise overlain on top of your sensor signal in the time series data.
This graph doesn't show it. These sensors are likely not installed near any large AC structures or power lines. But if you were to see that, you would see a 50 hertz or 60 hertz signal, something down right about here you can see on the frequency domain.
I assume there are other sources of noise as well. What could those be?
Yeah, it can be vibration, machines, impact. Really, noise can come from anything. We've had one client that was picking up noise that came in from aircraft flying overhead.
Interesting. So you could probably see it from a generator or from power tools.
Correct.
All right. So let's take a look at this report on the time series data. How does that translate into a spectral analysis after applying the FFT?
All right, so you've got the raw signal that comes in. That would be that vibrating wire that vibrates up and down. And then when we run the spectral analysis, you can see one predominant frequency here. In this case, the frequency is stated as 2,524 hertz. That is our main frequency. And again, that is what we are interested in. Do we have the correct signal? So let's take a look at some of the diagnostics now and help us identify, do we have confidence in this measurement? So the diagnostics in this case are down here. Let's just go through from the top. Frequency amplitude. That signal, it has an amplitude of 2.2 millivolts. That's a pretty healthy signal. Generally speaking, anything above 1, I'm not that worried about. That's a pretty standard signal coming from vibrating wire sensors. I'll occasionally see a few that are below 1. Again, not a big worry. We do have a threshold in the data logger that by default it's set to 0.01 millivolts. Anything less than 0.01 is identified as not a possible signal. It's too weak. That's a pretty small signal. It can happen, but generally speaking, greater than 1, I'm not worried. When it's less than 0.1, I'd like to see the graph at that point.
Okay.
The next diagnostic is the signal-to-noise ratio. This means that that signal is 6,372 times stronger than the nearest competing signal. That's pretty large.
That's a really powerful signal, isn't it?
Correct. My general rule of thumb here is I like to think about 3 is where I like to, if it's less than 3, I might go take a look at the graphs. If it
could be questionable.
Yeah, if it's greater than 3, I'm not too worried about it.
Okay.
In this case, 6,000, what that tells me is this signal is significantly stronger than any competing noise source.
Okay.
I'm just not worried about it. Let's take a look at some other graphs if we can here. Okay. Again, this one is also a textbook quality sensor. You've got one primary signal at 2,980 hertz. And I like this one because the signal-noise ratio is 3,364 times bigger than the nearest competing signal. That nearest competing signal is at 1,400 hertz. Again, it's well above 3. I'm not worried about it. I would expect this to be a very clean, strong signal. When you look at the graph, that's what it is. Let's take a look at some of the other signals. And the next one is going to introduce a value we haven't talked about in the diagnostics, and that's the decay ratio. In this case, the decay ratio is 0.1. Let's explain what the decay ratio is. The decay ratio represents how quickly that signal gets quiet. It's not one that I really stress a lot about. Vibrating wire sensors, if you get a bunch that come from the factory, they're going to have different decay ratios. It's not a big deal. It's just a way to look at it over time. In this case, this sensor stays with a strong signal for quite a while. The decay ratio is high. That's a really good sensor. This sensor I would also describe as a high quality measurement, but you can see visually the signal gets quieter quicker and the decay ratio is smaller.
Okay.
Does this concern me? Not in the least bit.
So that doesn't mean that the sensor is bad.
No, absolutely not.
Okay.
What concerns me is have identified the sensor frequency correctly. And the two most important diagnostics are what is the frequency amplitude and the signal noise ratio. This one's also a good one. The frequency amplitude is less than 1. But when I look at the sensor signal and a signal noise ratio of 600, it doesn't really concern me.
Just tells you got a good sensor. Believe this measurement.
Yeah, it's a good sensor. You can have confidence that the sensor output really was 2,513 hertz. Okay, now this is one of the graphs that was in question from your training. It looks a little bit unusual. You can see that in the time series. You have what doesn't look like a standard oscillation.
Right.
Again, I'm going to go back to what I've been saying. As long as I've got a sensor signal identified and I have a healthy frequency and healthy signal noise ratio, I'm not too worried. I have a high degree of confidence this is the right measurement from the sensor. But with that said, what's going on in the time series here? You probably have some sort of damping going on. Damping would be a resistance to that vibration. Damping can come from lots of things. On a car, it's a shock absorber. In a sensor, it might be the way it's clamped. It can be air resistance. There's all sorts of things that impact that vibration. That vibrating wire is a physical system, a mechanical system, and there are going to be things that change how it vibrates. Again, I'm just not worried about it. It's a clean, good quality signal, and that's what I like with VSPECT. I've got a very high confidence that we've identified the right signal.
So in this case, even though the time series graph is unusual, the sensor is still usable.
Oh, absolutely. This is a great sensor. I'm not at all concerned about this.
Are there instances where you can see that a sensor is not usable?
Yeah, and I've got some graphs a little bit further along. We'll show these here to you. This one is a really good sensor. The signal noise ratio is a little bit lower than what we've seen. This is 58. If you compare these to a couple of graphs sitting on your desk, you might say, well, that's the lowest signal noise ratio. Yeah, I'm not worried about it. It is 58 times stronger than the nearest competing signal. That's okay. It's a really good quality measurement.
Okay.
This one is a good one. This would be a little bit more of an example, possibly from an AC noise source. You can see we've really got two signals going on here, and you can see that in the time series. The first signal would be the vibrating wire sensor, and then the second signal is you can see this other frequency going on here with these unique peaks and valleys in the signal. When you run the fast Fourier transform on that, what you're going to get is the primary signal of the vibrating wire sensor, again, that has a strong amplitude of 1.6, and it is 13 times stronger than the nearest competing signal. That nearest competing signal is 2,900 hertz. You can see it right there at the base of the vibrating wire signal. What that means, the vibrating wire output is 13 times stronger than the noise source. Again, there's noise. Doesn't bother me. That's because we've got VSPECT in there. But when you look at that noise, this is a low frequency noise. That noise would come up here on the frequency spectrum down in your low frequency, likely in a 50, 60 hertz range. My guess is this is probably AC noise. But you have a series of these similar noises that are evenly spaced through the graph. That is telling me that this is likely harmonics from the primary noise source. Great, I can see it, it's there. I'm not going to lose sleep about this sensor. Back to the fundamentals with VSPECT. We've identified the sensor frequency. We have the diagnostics to look at and go, yeah, that's a strong signal response. It is significantly stronger than any competing noise. If I were to get this measurement out of a CR6, I wouldn't even be worried about trying to get a graphical representation of this. It's a quality measurement.
So if you were measuring this sensor with that noise, and you weren't using VSPECT, what would be the output? What would be the result of that?
So what you can have when you measure a sensor that doesn't have VSPECT is you can get different sensor frequencies identified on a non-VSPECT measurement. And the way people typically identify that is they'll plot whatever their engineering parameter there is. If it's a piezometer, it'd be pore pressure. They'll plot pore pressure and they'll see a random spike or a drop in the data, and that can be the influence of an intermittent noise, a noise that comes and goes. Those anomalies are typically filtered out of the data set by the person reviewing the data, and it's a time-consuming process to filter that out. That's one of the benefits of VSPECT is when it comes to the analytics and reporting on your data, you don't have to spend time filtering through and eliminating bad measurements. If the noise is consistently there, you may not have as good a quality of a reading, and you may see a little bit more of a jittery sensor. It can still represent the system it's measuring, but it's not going to be as consistent and the exact representation of what the system it's measuring is.
Okay. So whatever parameter it is that you're measuring, it could be misrepresented.
Right. Incorrectly identified or have an offset to it.
Okay. Very good. What other sensors do we have that we can look at that would show
I've got
anything meaningful here?
A couple other sensors. Again, the bulk of these are pretty good quality. There's just something different, so it seemed appropriate for this discussion. And I want to reiterate, when you look at these sensors, the majority of them are going to be really good quality measurements. The VSPECT filters out anything of concern, and it's going to work. This one is a little bit different. You can see here, everything looks good in terms of the measurement, the diagnostics. The frequency amplitude is less than 1. Not too concerned about that. That's still pretty darn good. But when you look at the time series graph, the whole graph has a slight offset from 0. Yeah. Not a big deal. Occasionally you'll see something like that. I'm just not worried about it. Again, I want to communicate that VSPECT gives you confidence in the measurement you get, or tells you whether you want to question further. I have confidence in this measurement. I'm not concerned. This is a good example of one where I would be concerned on it. So the VSPECT measurement came back with the sensor frequency was unidentifiable. NaN stands for not a number. And then the thermistor resistance came in at 678,000. Compared to a standard thermistor resistance, that's not right. That's tripping some red flags right there. So both of those make me question what's going on. When I look at the report with the graphs, what this really feels like is likely an open circuit or a damaged sensor. This could be a lightning damage sensor maybe. It could be a cut cable. It could be improper wiring. Something's not right here. This is not a measurement.
Yeah, clearly it looks different.
Yep. And again, this is another one. Same thing. You can see something coming in on the time domain. It really is just open circuit noise. It's just not what I would call a measurement. And VSPECT catches that. It says, yeah, this is not a number. It doesn't have diagnostics to report. This is not something you would want to see. This last measurement is kind of an interesting one. You've got a pretty clear signal here. When I look at the frequency domain, that to me looks like a sensor. I've got confidence in that. When I look at the time domain, it's got a little bit of a shift right here. You can see that shift in a little bit of a spike near 0 hertz. I'm not too worried about it. We've identified the signal here. But here's what does concern me, and I would want to watch this one a little bit more. We have identified the sensor signal, but when I look at the diagnostics, the amplitude is 0.01 millivolts. That's getting pretty low at that point. The way I would look at this is, can I change my input to the sensor and see a different output that makes me believe, yes, I'm actually talking to the vibrating wire sensor? So one of the things on the VSPECT report is it documents the excitation voltage. So why is that important? When you configure a Campbell logger to measure a vibrating wire sensor, we have the excitation voltage. Generally speaking, there are 3 options you can use: 2 volts, 5 volts, and 12 volts. If you don't know what excitation voltage to use, default to 5 volts, and you're going to be fine almost all of the time. 12 volts is what we reserve for really long cable lengths, and I would define that as getting several thousand feet of cable, or a noisy environment where you want to have a stronger sensor output to compete with the noise better. You increase your excitation voltage, you should see your signal to noise ratio go up. Or the third case where I use 12 volt excitation is a poor responding signal. In this case, this is a pretty weak signal. I would like to kick this up to 12 volts, and I would expect that frequency amplitude to get better. The last excitation voltage would be 2 volts. We reserve this when you want to keep the sensor signal really quiet so it can get quiet quicker. Basically, when you're doing a fast measurement with a CR6, you want to measure the same sensor every 1 to 2 seconds. Decrease the voltage excitation so that by the time you get to the next measurement, 1 or 2 seconds later, on the same sensor, that sensor has quieted down.
Excellent. So it seems like there are 3 main advantages to using VSPECT. One is the elimination of noise from your measurement,
Yes.
the sensor diagnostics,
Yes.
and being able to use it for long cable lengths or improving the signal from in a noisy environment.
Correct.
Okay, excellent. Well, Brent, this has been really helpful. Thank you very much. Appreciate the explanation. And thank you for joining us. If you have any sensor data that you would like to discuss, we're always happy to chat. Thanks for joining us.